This video contains the notes for section 8.5, which is one more integration technique, integration using partial fractions. So it's time for us to remember how to take a rational expression, let's say like this, 2x plus 1 over x squared plus 3x plus 2, and decompose this into partial fractions. You got to remember what that means and how to do it. Well, what it means is this came from, instead of finding a common denominator by multiplying two things together, we're going to sort of do the opposite. We're going to take the two factors of the bottom and split this up into two fractions that would have added up to give us this fraction. Now, the first thing we have to do is factor the bottom to figure out what those two different denominators would be. So, in this case, we have two different fractions. One of them has a denominator x plus 1, one has denominator x plus 2, and if we get a common denominator here, we'd multiply those together, and our common denominator would be this. The question is, what would these numbers have been to give us the 2x plus 1 on the top? And to figure that, we say, well, if I actually wanted to reconstitute this now, this right here is missing, to get the full denominator here, it's missing the x plus 2. So I'd have to multiply a times x plus 2 on the top, right? That's missing there, over the common denominator. And this is missing the x plus 1. So I'd have to multiply the top and bottom of that by x plus 1 to get that common denominator. I already had the x plus 2, right? But I needed to multiply both by x plus 1. And then we see that distributing this, I get ax plus 2a, distributing here, plus bx plus b over x squared plus 3x plus 2. And that means that this must somehow match up to this. Well, here are the x coefficients. So let's see, that means ax plus bx must somehow give us the 2x. Or in other words, a plus b must be giving me the coefficient of 2. Right? I don't actually want the x's in there. ax plus bx equals 2x, so the x's disappear. So the a plus b must be contributing to give me that 2x's there. And likewise, the 2a and the b, the pieces without any x's on them, must be adding up to give me the 1 here. So 2a plus b must be equal to 1. This is a little 2-by-2 system, so you can solve this using substitution or elimination or whatever you want. I think the easiest thing to do here would be multiply this equation through by -1, and then add. That gives me a is equal to -1, and then plugging that back up here, that must mean that b is equal to 3. Right? So it turns out that my original fraction, this means that 2x plus 1 over x squared plus 3x plus 2 must be equal to minus 1 over x plus 1. There's my minus 1, plugging that in for a, plus b, which is 3, over x plus 2. All right. Now, what does this have to do with calculus? Well, this turns out to be a useful integration technique when we have problems like this, because if I had been taking the integral of this, finding its antiderivative, I wouldn't be able to do this. You could try u substitution, but there's no way to get things to match up the right way. So instead, we break it up into these partial fractions, and we integrate one at a time. So what's the antiderivative of 1 over x plus 1? Well, that's just the natural log of the absolute value of x plus 1. And the antiderivative of this, bringing the 3 out to the front, it's just the natural log of x plus 2 plus c. So that's where that gets us. And notice here that I didn't do any u substitutions here. As long as this is just an x, you're okay. If this had been a 2x, then I'd have to have like a 1/2 here, right? Just like when we were doing our integration by parts, our tabular integration. If you have something here on the x, as long as it's just a linear multiple of the x there, you would just end up dividing by that x. And you can do a u substitution if you want to support that. Okay, so let's do a couple more examples. Let's find, we know what the antiderivative of 1 over x squared plus 1 is. That's tangent inverse, right? But what about the antiderivative of 1 over x squared minus 1? Well, we would say here, sometimes just do this work off to the side. Say, let's see, that's a over x plus 1, b over x minus 1. Right, that's the, those are the two factors of the bottom. So doing our multiplying here, that gives me a times x minus 1 plus b times x plus 1 must be giving me the 1 that's on top there. You can put the denominators in if you want, but they're not going to, I mean, they're the same, so it don't really matter. Say it's over my common denominator. So this must be giving me the 1. So let's distribute the stuff on the top. Ax minus a plus bx plus b is equal to 1. So looking at the x coefficients, there are no x's here, which means that the a plus b must be 0, no x's. And here I have minus a plus b, that must be giving me the 1. Those are all set to cancel out, so I can add those together. I get 2b is equal to 1, so b is 1/2. And if a and b add up to 0, that means that a would have to be negative 1/2. So, now that I have those values for a and b, I can go back and rewrite my original integral as minus 1/2 times 1 over x plus 1. I like it better like this than having the 1/2 on top of the fraction, but you could write it like that. I think it's just a little more confusing. And then b times 1 over x minus 1. And then taking the antiderivative, just bring the fractions out to the front. The antiderivative of 1 over x plus 1 is the natural log of x plus 1 plus 1/2 natural log of x minus 1 plus c. And you very well, that's a perfectly acceptable answer if you're writing the answer. But using a little bit of logarithm stuff, I just want to show you one other thing. Might help you match it up to a correct multiple choice answer. I could factor out a 1/2 here, and then rewrite these with the positive 1 first. Natural log x minus 1 minus natural log x plus 1. So I changed the order and I factored the 1/2 out. And then you know when you subtract logarithms, that's the same as x minus 1 over x plus 1. Remember, subtraction can turn into division like that. So that's another way of writing the answer. But notice, to do this factoring, the only reason we were able to do that is the 1/2 actually did factor out and moved out to the front. Okay? I think that should suffice. 2 examples there. When do you know that you're supposed to do this kind of integration now that we have so many different techniques? Well, if the bottom can factor and a u substitution won't work and it doesn't match up to tangent inverse, then this is the method to use. All right.